So today, I'm going to talk about the construction industry, as I hear that many of y'all are looking forward to joining it when you get older, and the keys to succeed in it. So the first key to succeeding in construction is knowing how to build with steel, wood, and concrete, as these materials form the bedrock of our industry. The second key is networking.
Ring, 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 ring.
It's embarrassing, sorry. Hello?
Hey, this is Mark from Pioneer Contractors calling about your upcoming project.
Hello, Mr. Mark?
Well, unfortunately, the forest where we source our wood from is just burned down a few days ago. And because of the high inflation, the prices of steel and concrete have risen by 200%, resulting in a shortage of building materials. Due to this shortage, we'll have to delay building your house by 4 years.
Wait, but didn't we agree 2 weeks ago that we'd start building in June? Isn't there somewhere you can procure materials or any reserves?
I apologize, Mr. Muhumuza, but we have been forced to delay the builds of all our clients due to the current circumstances. The only solution I can offer would be to build with alternative materials, but I cannot guarantee you that the strength of the house would be solid if we choose to go that route.
Okay, thank you. Have a good day. No wood, no steel, no concrete. How else am I supposed to build this home? How about earth? As termites use mud to build their homes, I mean, look at that massive structure. Isn't that impressive? And how about wasps as well? As wasps also build their homes out of mud. And if mud can safely house these creatures, why don't we as humans build with mud? Seriously, who wouldn't? Mud is cheap, since it's already there. It's present in large quantities all over the earth. And a cool thing about earth is that it has a high thermal mass, meaning that it can absorb heat and release it slowly, ensuring that the temperature inside a building will remain at a moderate temperature, which means that you have to spend less money heating and cooling the house. However, Earth's exciting potentials does not come without its drawbacks, as building with earth requires a lot of manual labor, as much of the work of compacting the earth and even forming the bricks to make the home is done by hand, which is a lot of work. And second, and more importantly, is that earth is naturally weaker than steel and concrete. Thus, my research group and I sought to strengthen earth by applying the techniques used by mud dauber wasps to strengthen earth. Now, mud dauber wasps are a common wasp, and they build their homes out of, unsurprisingly, mud. And they build their houses by carrying balls of mud to the nest site and plastering it in layers in a tube-like shape. And as they plaster layer after layer in their nest, they repeatedly tap their nest with their legs and mandibles, producing vibrations. And these vibrations compact the mud and they strengthen the nest. And since vibrations were able to increase the strength of a mud dauber's nest, we believe that applying vibrations to earth will also strengthen it for our home. Thus, my research group and I tested this idea by designing and creating samples and conducting strength and density tests. To do this, we first crushed dried soil using a mortar and pestle. Afterwards, we combined this crushed soil with sand and water in an automatic mixer for 2 to 3 minutes, and voila, we had mud. And this mud was placed in our 3D printer, which worked like your average 3D printer, except it just printed mud. And here's a quick example of how it works. It's quick, efficient, and rather neat. For 4 of the samples, they passed through a piezoelectric actuator, which sounds like a cool fancy name, but all I just did was I converted electrical energy into vibrations. So the piezoelectric actuator was composed of 2 metal plates connected to a circuit board. So the actuator pretty much could produce vibrations in the metal plates. So we were passing mud between vibrating plates. Then for 3 of the samples, we simply printed them out regularly without touching them. And then afterwards, we let the samples air dry for at least 7 days in the lab. Then afterwards, we conducted penetration resistance tests, which measured how much pressure a sample could withstand before ultimately breaking. And to do these tests, we cut the samples, as pictured on your left, into 1-inch segments, and I crushed them using a fruit penetrometer, as pictured on your right. And the fruit penetrometer measured how much force I used to break the sample. And this force reading was then converted into a pressure reading. And after we conducted the penetration resistance test, we conducted density tests using the crushed pieces of soil. And in order to perform this test, we first would weigh the crushed piece of soil, then coat it in wax, then weigh it again, then drop it in a container of water to determine its volume. Then we took all these values to calculate its density. Now, conducting both of these tests produced results as shown behind me. It initially seems that vibration does improve soil strength, as the compacted samples in orange, which are the samples that would pass between the vibrating plates, seem to have higher strength values than the uncompacted samples in blue, those that didn't receive any vibration. Then when we take a closer look at the density, we see that they have very similar densities. And after further analysis, we further concluded that vibration has no effect. We conclude that vibration has no effect on soil strength. And while this may seem disappointing, my research group and I hypothesized that this was because our samples were just too thick. Because the mud was so thick, the vibrations couldn't truly penetrate through it. And we look forward to performing the same test on thinner samples in hopes that the vibrations will actually be able to penetrate. However, this is not the end of building with alternative materials, as there are several other promising options that are awaiting our use, such as cork and mycelium. Cork, the stuff in your wine bottles, can be heated up to form a very durable material that is both water and heat resistant, whereas mycelium, also known as fungi, with its roots can bind matter strongly together. In fact, producing steel and concrete each year emits roughly 4.9 billion tons of carbon dioxide into the atmosphere. And this carbon dioxide goes up to the air and further contributes to the greenhouse effect. It is also absorbed by our oceans, where it acidifies the water, harming both the fish and organisms that live in these waters. And our main reason why our emissions for steel and concrete are so high is because of our heavy reliance on these materials. And if we don't change this trend, we risk drastic changes in temperature and poor air quality, which will affect our agriculture, ocean levels, and other areas of our lives. However, we can prevent this change by looking to nature to build our future. By building more and more with materials already present in our environment, we can reduce our reliance on steel and concrete, and thus our total emissions. And I hope as we build more with these materials found in nature, we feel inspired to look to nature for the solutions to the problems we face in engineering and science. For engineers searching for a way to stop water in a river, or for scientists searching for a product suitable for the production and storage of honey, I say look to nature. I say look at the intricate arrangement of branches beavers create in their dams. I say look at the intricate honeycombs that honeybees create in their beehives. Regardless of the situation, regardless of the problem, the answer lies in nature.